All right. Is there any questions before we get started? Okay. Just make sure you know the Lab 8 is due end of today, the write-up. And the Lab 8 is about amplifier, and amplifier is one of the important part in your final project. So make sure you do understand how the Lab 8 experiment works. Okay. All right, and let's see. I think most of the grading of Lab 5 and also Lab Practical should already published. If you have any question about your grading, you can email us. And also for the, just make sure you know all of you should do the AD2 version. Okay, just make sure you know that. All right, let's talk about today's lab. All right, so this week is today's Lab 9, which is step response and timing circuit. So what's a step response is the voltage response of a RC circuit and also the RL circuit. So make sure you read the manual before the class starts. Okay, so here the figure 9.3 is the step response for a capacitor. The left one is the voltage response, and the left one, the left one is voltage response, and the right one is the current response. The curve in here, or the plot here, follow the equation 9.6 equation. Okay, so it's the VC in here is the voltage cross capacitor, and the Vs is a source voltage. This is a circuit diagram. Okay, and then the T0 here is the time is start to charge. Okay, then RC is a value of the resistor and capacitor. Okay, so make sure you do remember this equation, or you know where to find this equation in the manual. Okay. Then for the RL circuit, okay, so which is the circuit looks like here, and here is the equation, current equation for the RL circuit, and inversely, the voltage for inductor RL circuit is decreasing when the inductor start to charging. Okay, and then the current start to increase when the inductor start to charging. So this is not too hard to understand, because essentially capacitor is two metal plate. So when you start to charging them up, at the end it will be like an open circuit. So the voltage will be equal to, or almost very close to Vs. It's never going to charge until exactly Vs, but will be very close to Vs. Okay, so that's the step response for RL and RC circuit. And there's another very important component in here is a time constant. Okay, so I will talk about that when we go to the tasks. Okay, then is the timing circuit. Okay, so I may not going to go through all the theory here. Make sure you know the 5.5 timer is a very functional chip, and you're going to learn there are a couple basic functions for this chip, and you may need this chip in the future class. Okay, for example, in your senior design, you may need this chip to design something. Okay, so basically this is a circuit diagram of the timer chip. Okay, so you should already say this since you should already done the pre-lab. Okay, so basically the input is a 2 comparator and go to a SR large. SR large is a very basic digital circuit. Okay, and then here is the output with a buffer. All right. So the 5-5 timer, there are 3 modes. Okay, one is a stable mode, which can work as an oscillator, which oscillator is generating a period signal. Okay, then there is a monostable mode, which can work as a like single one-shot pulse. Okay, so what that means is something looks like this. Okay, only generate one pulse of signal, and also there is a bistable mode. Okay, so that's the lab menu. Let's go to the tasks really quick. Okay, so this is tasks for this week. Okay, so there are 3 tasks. The first 2 is pretty similar. You're going to build this circuit and measure the value for the capacitor and also the inductor in task 2. Okay, so all the value is already given. Okay, so let's see. You're going to use the function generator to generate a square wave and with a reasonable frequency. So what's the meaning of reasonable frequency? Is something looks like this. After you build this circuit, okay, you're going to measure the Vs and Vc by using the oscilloscope, and ideally, the output voltage of Vc will be something looks like this. Okay, it's going to when the Vs turn on, the capacitor start to charging, and then it's going to the voltage will be almost a flat line, and when the Vs start turn off, the capacitor start to discharging. It's something like I'm charging again and then discharging. Okay, but if your frequency is too high, okay, what will be happen is something looks like this. When the capacitor starts to charging, it's not going to fully charged. Then the Vs start to turn off. Okay, then it start to discharging. Okay, so that's because of the frequency is too high, and there's the time is not enough for the capacitor to fully charged. Okay, so if you have something like this, you may not able to see the time constant point. Okay, so what you need to do is you need to reduce the frequency and until the capacitor can be fully charged. Okay. All right, so after you build the circuit, as I mentioned, you will see something looks like this when the capacitor start to charging. Okay, so what you need to do is you want to measure the time constant. Okay, so what's the time constant is when you have the voltage cross the capacitor. Okay, so voltage start to increasing. When the voltage increase until 0.632 times Vs until this voltage, that's the one-time constant. So the time take the capacitor charge until this voltage, that's a time constant. So after you get this plot, okay, so you may have very many period of this plot. You want to only take one of the period or the charging plot right here and zoom into this part. And you want to measure the voltage from 0 to this point by using cursor. Okay, so you have 2 X cursor at here. And then you want to use Y cursor to measure when it starts to charging and until this point. So that will be one time constant. Okay, so that's how you're going to use cursor to measure the time constant tau here. So after you measure the time constant, you know the RESR and you know the RS, you can calculate the capacitor. So the, and also the R sense. The RS in here is the internal resistance of the function generator. Again, since you are using AD2, RS is equal to 0. Okay, so just R sense and RESR. Okay. So that's how you're going to use the oscilloscope and the cursor to measure the time constant and then calculate the C test here. Okay. All right. So the last two steps here is step 10 and step 11, which is export the data from the oscilloscope, and you can plot it in the MATLAB or even in the Excel. Let me show you how to do this really quick. Okay, so this is your waveform. Okay, so after you have your, I just give some demo here. So after you have your plot of your voltage across the capacitor, what you can do is you can export the data. Okay, so this is the data points of your signal. So this is there are 3 columns of data. One is timing, which is start from this point right here until so from the left part of your screen to the right part of your screen. So that's for my screen is from 95 millisecond to 5 millisecond. And then the other 2 column is voltage of channel 1 and the voltage of channel 2. So basically time is the x-axis and the channel 1 and channel 2 is y-axis. Okay. So then you can save the data. Okay. So something looks like this into a Excel plot. Excel document. Okay. So then you can plot the waveform. Okay. So if you check the step 11 is asking you to plot the ideal step response and also the measured voltage data. So what you're going to say is you can use the equation in the lab menu to plot the ideal step response. It may something looks like this. Okay, but when you plot the measured data, you may have many periods. Okay, so you may have something looks like this. So this is the ideal plot, and your measurement plot may something looks like this. Okay, so that's your merit plot because you have many periods in your screen. So what you need to do is you need to make sure you can align them together. Okay, so you can say they can start charging at the same time. Okay, so that's your T0. Okay. Okay, so that's how you can compare the ideal plot and also the merit plot. So you can either do this in the Excel or MATLAB to make sure you choose the data when the capacitor start to charging, or when you take a screenshot in the oscilloscope. When you export the data, you put the left part of the oscilloscope to be when it start to charging. Okay. Okay, so just make sure you align them together and compare them in one plot. Okay, so that's all for task 1. Okay, then task 2 is pretty much similar. you are going to build the same circuit, but just change the capacitor with the inductor. And what you probably will see is this plot right here. Okay, so don't worry, that's not meaning you did something wrong because you only see this peak here. What you need to do is you want to zoom in this part. Okay, so then you can see the charging plot, which is the voltage across the capacitor. So how you can measure the time constant for the voltage of the inductor. So this is a voltage across the inductor when it start to charging. So what you can measure is you can measure start from top and until 0.632 of Vs. Okay, so this will 0.6 of Vs. Then you can use Y cursor. Y cursor to measure the time constant. So this will be the top right here. Okay, or what you can do is you can use mass function. So there's a mass function in oscilloscope. You can use Vs to minus Vl. Then you will get similar plot as a capacitor charging plot. Then you can use the same way to measure the time constant. So either way works. So you can use both way. You can get the same time constant, and then you can use the equation to calculate the inductance. Okay, so for the capacitor is tau equal to RC, and for the inductor RC circuit, RL circuit is tau equal to L over R. Okay. And then step number, in task 2, you don't have to export the data. Okay, just for task 1, you need to export the data. Okay, and another thing here, RESR, that's the internal resistance of the inductor and the capacitor. Okay, so you don't need this resistor when you build this circuit. Okay. Okay, so that's all for task 1 and task 2. Any question about these two tasks? Okay, then task 3 is light doorbell design. Okay, so which the circuit schematic is actually already given. Okay, so that will be the circuit you're going to build on the breadboard. Okay, so before you build the circuit, you do need to calculate the value for R1 and C1. Okay, the R2 is already given. It should be 10K. It's given, yeah, here, 10K for R2. But you need to calculate R1, C1. So it's asking you to calculate R1 and C1 such that the RC charge will take 5 seconds until the two-thirds of the VCC. Okay. What you need to do is you can use the RC charging equation, as I mentioned in the menu, to calculate the value for RC. Okay, so at the end, if you calculate everything correctly, the RC will have an equation related to the T, which is the charging time. Okay, then you can plug in T equal to 5 seconds, then you can find the RC value. Okay. And another thing you want to know here is you want to make sure R1 not too very large. Okay, so R1 probably, let's say, smaller than 300K ohm, because the reason is you want to measure the voltage across at the threshold at the end by oscilloscope. Oscilloscope itself have some internal impedance, okay, or the input impedance. So what will happen is something looks like this. There's a let's see. So this is a C probe, R probe. So this will be the circuit diagram when you have a probe in here, is something looks like this. That's R1 will be parallel with R or in series with RP, the input impedance of probe. So that will cause some loading issue if your R1 is very close to this value. So that will cause loading issue. So make sure your R1 is smaller than 300 kΩ to avoid a loading issue. Okay. Okay, so after you have all the value, you can build this circuit on the breadboard. So make sure you include the 313 ohm resistor to don't short make sure the LED doesn't short. Okay, and also another thing is the 55 timer chip pin out is different from this circuit diagram here. Okay, so make sure you do check the data sheet, the pin out on the data sheet to build this circuit. Okay, the last thing in the schematic here is the switch right here. Okay, so you may have the push button in your lab case, or you may not. So it doesn't matter if you don't have the switch button. What you can do is you can use the wire from your lab kit and work as a switch. So this switch is not the switch we use to turn off and turn on the lights. So this switch is a push button, as I mentioned. So what will happen is you want to plug in and plug out. Then that's how this switch works. So if you use a jumper from your lab kit, so you need to plug in, make it short to ground, and then plug out, make it open with ground. So that's how the switch in here works. Okay, and so what will happen after you build this circuit and turn on and turn off the switch is you will see the LED turn on for 5 seconds, and then it will turn off by itself. Okay. So when you use oscilloscope to measure the voltage at the output and the threshold, which is this pin and this pin right here, you will see this plot right here. Okay, so the channel 1 is the output, channel 2 is the threshold voltage. Okay, so you want to use the row mode to measure these two signal, and you will see something like this. If you see something like this, you pause your signal and use the cursor to measure the period of this pause. Okay, so it will be 5 seconds if you do everything correctly. Okay. All right, I think that's all for this week. Any questions? Okay. If not, you can do your experiment and I will open the breakout room. Okay.